Draw the shear and moment diagrams for the beam. Indicate values at the supports and at the points where a change in load occurs. To begin, first of all, let's convert our distributed loads into point loads. So from beginning of this beam, at left-hand side till point A, we're going to have a triangular load, so 0.5 times 1.5 times 4, which gives us 3. And because the other side is symmetrical, the other side is going to be 3 kilonewtons as well. And between A and B, it's going to be 2 times 4, which is 8. And the distance between B and the point load is going to be 1/3 of 1.5. Comes up to be 0.5. And so it's going to be the other side. Now we can find our external reaction forces at A and B. Ax is going to be 0. Let's take a moment about the point B. Find our solution for vertical reaction at A. We're going to have clockwise 3 kilonewton and it's 0.5 meters away. And then we have counterclockwise 8 kilonewton and it's 2 meters away from B. Then we have clockwise AY 2 meters away. Pardon me, 8 is 1 meters away and AY is 2 meters away. And then finally we have counterclockwise 3 kilonewton and it's 2.5 meters away. All equals to 0. Solving for AY, we get a solution as 7 kilonewton. Now we can sum the forces in vertical direction in order to find our solution for BY. So we can have negative 3 kilonewton, positive 7 from AY, negative 8 from the rectangular uniform distributed load, and then our unknown BY, and finally negative 3 kilonewton, all equals to 0. Solving for BY, we get our solution as 7 kilonewton. Well, we could have done this by symmetry as well, but I thought it's better to have it solved. Anyways, now that we have all the values, we can start drawing our moment diagrams. So for our shear, we're going to begin at 0. And then we have our first uniform load, which is triangular. And it's going to go downwards all the way till 3 kilonewton. And our curve is going to be second order, and it's going to concave downwards. Then we have our external reaction force of 7 kilonewtons, so we're going to go up 7 kilonewton, and we'll stop at 4 kilonewton. By the way, this diagram is not to scale, but it gave us the general idea. And then we have a uniform distributed load of 8 kilonewton going downwards. Because this curve is 0 order, our shear curve is going to be first order, and it's going to go down till negative 4 kilonewton. And then we have our external reaction on By, which is 7, so we're going to go up till 3, because negative 4 plus 7 is positive 3. And then we have our triangular uniform distributed load, which is first order, therefore our shear curve is going to be second order. And because our load is increasing, our curve is going to be concaving upwards, and it's going to be second degree curve. This is our first order. Okay, so now that we have those, now we need to determine our point of intersection here. To do that, we can use our equations. Our equation for this area, which is between 1.5 meters and 3.5 meters. So our load equation is going to be simply -4. Then our shear is simply the integral of the load, which is going to be -4x plus a constant. Constant in this case, we looking at our shear diagram, we know is going to be +4. So now we can use our shear equation to find our solution, which is going to be when our shear is 0 in this area, we need to determine our value for our x. Pardon me, I did one thing wrong here. We'll have to go back a little bit to find our value for constant because I was trying to take a shortcut and I just realized when I was trying to solve for our x that that's not the right way or not the right shortcut. To determine our value for the constant, we'll have to assume that our shear is 4. Well, not assume, it's given from our shear diagram. So our shear is 4 when our x is 1.5. And constant is unknown. So solving for constant, we get our solution as 10. Now we can use our newly found equation to find our solution where the intersection happens. So when shear is 0, and that's the reason 1.5 and 3.5, we have -4x plus 10. And solving for our x, we get our solution as 2.5 meters. Therefore, our intersection is at 2.5 meters. Okay, now that we have this, we can move on to our moment diagram. Our moment will begin at 0 because there isn't any moment on this beam from the left-hand side. Now that we have our beam moment, we know that our moment curve for our first half, which is 1.5 meters long, del A, is going to have third order curve, and it's negative, or at least the shear is negative, and we need the shear area to find our curve. And the area for this parabola is simply 1 over 3 times the depth, which is -3, times the length along for the shear, which was 1.5. Solving this, we get our solution as 1.5 negative. Another way to solve this is we could cut our beam at point A, where we're going to have shear, which we already, well, we don't need to determine for our calculation for the moment. We can have moment at A, then we have our external reaction force or the uniform distributed load, which we converted into point load at 3 kilonewton, and we can just take the moment about the point A and solve for the moment A. So we're just going to simply moment A plus, because it's counterclockwise, 3 kilonewton, and it's 0.5 meters away, all equals to 0. Solving for moment A, we get our solution as -1.5 kilonewton times meter. So that's one other way to solve for this. Okay, now that we have that, we know that at 0, somewhere along this graph, we don't know where, at 0 moment graph flattens. We'll see where it is. But for now, I'm just gonna make a mark here. And because this is first order, we can determine our area here easily, which is basically area of triangle, which is 0.5 times 4 times 1, because we already determined our point of intersection. And this comes up to be a 2. So this means this flattening, I'm going to decrease it a little bit, happens at zero point 0.5. This we know. And now we know that our curve here on the shear diagram is decreasing, positive decreasing. So this means we're going to have concaving downward slope for our moment diagram. And this curve is going to be our second order curve, and this is our third order. Okay, and then on the other side, we have our negative area, which is symmetrical. So therefore, we're going to have concaving downward slope on the moment diagram on the opposite side of our other slope, which we just drawn. And this is also second order. Now that we have done that, we know that this area is under second order curve. So we can, and it's symmetrical in terms of the other area, but just for visual purposes, I'm going to use our formula again. So 1/3 times the length of the beam, or the length of the shear, 1.5 meters, and our shear, which is 3. Solving for this, you get 0.5, and 0.5 gets us to 0. So, and to determine the concavity up or down, we know that this area is positive and it's decreasing. So therefore, we're going to have concaving downwards slope. And the curve is third order. Okay, now that we have solved for this, we still need to determine our intersections between the section 1.5 and 3.5, or you can say A and B. To determine that, we need to once again find our moment equation, which we just gonna continue solving from our shear equation. So our moment equation is going to be negative 2x squared plus 10x plus c. Now to solve for our constant c, we know that when moment is negative 1/2, our x is 1.5 or 1/2. Solving for c, we get a solution as negative 12. Now we can plug our value of this c into our moment equation and determine where the intersection occur. So we can have moment x equals to 2x squared plus 10x plus, negative 12. And we need to determine where moment is 0, the value of x. Solve for this quadratic equation. Get our solution as 2 and 3. Therefore, these intersections. Draw the shear and moment diagrams for the beam. Indicate values at the supports and at the points where a change in load occurs. To begin, let's convert our distributed loads into point loads. Because they're symmetrical, just need to solve for one side, and it's going to be 6 times 2, which is 12 kilonewtons. And both of these are 1 meters away from point A and B respectively. Okay, and now we can find our external reaction forces. Ax in this case is 0, vertical at A is unknown, and vertical at B is as well. Okay, now we can solve for our external reaction forces. First of all, we can take a moment about the point B. Find a solution for AY. So we're going to have clockwise 12 kilonewtons 1 meters away. Then we have our unknown AY clockwise 2 meters away from B. And then we have our counterclockwise 12 kilonewtons and it's 3 meters away from B, all equals to 0. So for BY we get a solution as 12 kilonewton. Similarly, you're going to get a solution for AY as 12 kilonewton because both are symmetrical. Now we can start drawing our diagram, our shear diagram. To begin, our shear is going to start at 0. Del AY, we're going to have a downwards first order curve del negative 12. And then AY brings our curve up to 0. And it's going to run along 0 shear till B, where B bumps it up to 12 kilonewton. And from 12, we simply comes down with first order curve to 0. Now let's come down to our moment diagram. So for a moment diagram, we're going to start or initiate at 0 moment. And then as we proceed towards point A, we have negative shear and we need this shear's area in order to determine our second order curve for the moment. It's going to be negative somewhere here. So the first order curve formula is basically area of the triangle, so which is half times negative 12 times 2. And this gives us negative 12. And because our shear curve is negative and it's increasing, it's going to be concaving downwards like so. And then we have no moment till our point B. So we can have a straight line or zero order curve, you can say, till negative point and 4 meters in to the beam. And then at this point we have our positive shear area, and same as before, just same or symmetrical as our first triangular area, but with the opposite sign. And with that, what this means is that our moment is going to be positive 12, which will bring our moment to a 0. And our curve is, because this shear curve is positive and decreasing, the curve is going to look something like this, concaving downward. And both of these are, by the way, second order. This is the 0 order. And with that,